I'm very pleased to introduce Dr. Irene del Real to the Ore Deposits Hub family. Most of you will have seen her brilliant presentation last year in the early career session. Irene earned her degree in geology from the University of Chile with a master's degree from the University of British Columbia in Canada at the Mineral Deposits Research Unit, and a PhD degree from Cornell University in the US. Having worked on porphyry deposits and more extensively in iron oxide copper-gold deposits, her research focuses on understanding the genesis and evolution of hydrothermal deposits from a multidisciplinary approach, integrating petrological, structural, and geochemical work. Currently, she works as a postdoctoral researcher for the Millennium Nucleus Center of Metals Tracing along Subduction at the University of Chile. She is also, I believe, our first repeat speaker in Ore Deposits Hub, having given a stellar talk in the early career session from the first few months of ODH, after which we recruited her as a host, and now she has entered the main stage. So with that, Irene, I'm going to turn the floor over to you.
Thank you so much, Neil. And I'm very excited to be giving a longer talk today. And I'm not going to be talking about the same thing I talked last year, but it's sort of like a continuation in the same subject of IOCG deposits. So the title of my talk today is Formation of Giant Iron Oxide Copper-Gold Deposits by Superimposed Episodic Hydrothermal Pulses. And this talk is part of a very recent published paper and Nature Communications, Earth and Environment. So if you have further questions of the methodologies more in detail, I also invite you to read the paper. Everything is pretty well explained there. So just to start, why do we care about iron oxide copper gold deposits, better known as IOCGs? Well, I like to think that the future is going to be mainly renewable energy. And that means that we need a lot of primary resources, we need a lot of metals, and here are some of the main metals for wind energy and for solar. And as you see, iron ore and copper are two of the most important metals that we need in this kind of energy for the future. And also rare earth elements that are not here. And all of these, actually, we can find them in an IOCG deposit. So in that sense, we do care about IOCG deposits because they host metals of great interest for our future. So IOCG deposits, what, when, where, and how? Well, this type of deposit are widely distributed around the globe, as you can see on the map, and also widely distributed around time. So we have really old IOCG deposits, such as the one found in the Carajás district in Brazil, that are from the Archean. And we have some peaks between 1.8 and 1.5 billion years, specifically more in Australia. And then the youngest IOCG deposits form part of the iron belt in the Andes, which is where we're going to be focusing this talk. So it's a controversial type of deposit in the sense that there's no consensus on how they form, which is great because we'll get to do more research about it. And they contain economically significant amounts of copper and gold, of course, but also other elements of interest like uranium, nickel, cobalt, rare earth elements, etc. They're, of course, rich in iron oxides. This could be magnetite and or hematite. They have a really strong structural control. So in this sense, it's really important to understand our structural geology when we're looking for IOCGs or we're trying to understand how they form. And finally, they're not necessarily related to an igneous intrusion. So this is a pretty big difference from porphyry deposits. In that sense, I always love using this slide, especially when I'm talking about IOCGs in Chile. You know, Chile is like porphyry world. So IOCGs, we are like the secondary character for now. But it's always confusing when people start looking at IOCGs because our mindset is kind of just like thinking about porphyries. So I like to highlight that an IOCG is definitely not a copper porphyry. Why? Well, there is no igneous intrusion that is obviously the source of the hydrothermal fluids, and this is a controversial one, but up to now, we don't see mineralization hosted in an intrusion that we know is the source of the hydrothermal fluids. That means that mineralization can actually be hosted in rocks that can be millions of years older than the main mineralization event. And again, as I mentioned before, there's no unique model for IOCG formation, and I don't think there ever is going to be one, so that is fine. And so we have to think about this more as the processes that form an IOCG than just trying to look and pin down an exact model that will explain all IOCGs. So IOCGs in general have these really close cousins that are called iron oxide apatite deposits, better known as IOA. They're close cousins because both deposits typically occur broadly contemporaneous or one just after the other. One great example is Mina Justa, in Peru, where we actually have an IOA deposit, and overlapping it just like a few kilometers beside, we find an IOCG one, which would be Marcona and Mina Justa. But in general, the main IOCG or IOA districts in the world tend to have both deposits. We can think about the Olympic Dam district, the Andean Belt, or even the Kiruna district. So it has been proposed, various authors have been talking about this, that so something similar of what we see in porphyry and epithermal deposits, where in this case, the IOA deposit would represent the roots of the IOCG system. So this is a figure from Barra and company from 2017, where they show that the roots of the system would represent the IOA, like end member. And then as we transition up in the stratigraphy, this could transition to an IOCG deposit. At first magnetite rich, and if we go even upper, we will find an hematite rich deposit. So we have this IOCGs. Again, we don't have this igneous intrusion associated to it, so that kind of leaves us with not that many tools to characterize fluids and characterize the evolution of the deposit. So in this sense, how can we understand more of these IOCG deposits when there is no associated intrusion? So in this sense, I like the use of proxies. And as it says here, the utility of geochemical proxies requires chemical analysis of geochemical samples. Since there is no means of directly measuring past, in the example I'm going to show here, climates or environments, that could be like, for example, I like showing this example of a tree that has rings, and we like seeing the rings of the trunk of the tree, and we can use that, for example, to understand the past climates and environment. In this case, we will use a proxy, a geochemical proxy, to understand the evolution of a hydrothermal system. So in this sense, we're going to be using mineral chemistry, and that's going to be our proxy. And in this specific case, we're going to be talking more about actinolite. So I also like showing this figure over here, where we see a beautiful image, a map of a pyrite, and we can see something pretty similar than these rings that we see here in the tree. Looking, in this case, at the composition or the concentration of copper in a pyrite. So going back to the Andean IOCG deposits, well, these deposits form part of the iron belt of the Andes that goes from sort of like mid-Peru to mid-Chile. It's composed by IOCG deposits and IOA, so we find quite a diversity in that sense. The part of Chile, as we can see in this map, some of the most important deposits here is Candelaria, Manto Verde. In the IOCG world, we find Los Colorados, Algarrobo, Romeral in the IOCG, in the IOA world. And if we do assume, we're going to be working or looking at data in this presentation specifically from the Candelaria Punta del district, Punta del Cobre district. This district, if one sees it as a whole, is actually the largest IOCG district of the Andes, which makes it a pretty important one. And currently it has 9 different active mines that are working in the district. So it's a very active one in general. The mineralization here is mainly hosted in volcanic rocks from the Punta del Cobre deposit. This is a lower Cretaceous volcanic formation. And on top of it, we find a rather large sedimentary marine basin that we call the Chañarcillo Basin, which we can divide in different formation or units. Towards the northwest, we find a large batholith that we call the Copiapó batholith, which we can divide in 3 main intrusive units, where the San Gregorio one, that is this dark purple one over here, has actually the same age of mineralization than the Candelaria main copper event, which is 115 million years old. So again, we're like in lower mid-Cretaceous. This specific timing for the event has been dated using rhenium osmium and molybdenite, and also uranium lead in different dike that we find in the area. So it's a pretty well constrained mineralization age. This is very structurally controlled. So we can see in the map actually a lot of these north-northwest sinistral strike slip faults. And most of the mineralization is actually following these faults. And again, as I mentioned before, structural geology is really important for IOCG systems, and the same is for this case in Candelaria. So just a little bit about the alteration normalization styles we observe in the district is that it's very lithology dependent. So the alteration is going to look very different if we are in the lower volcanic unit versus if we are in the upper sediments. So in this sense, it's pretty widespread. And it's a very disseminated pervasive alteration in the lower andesitic unit that hosts the main mineralization. And we can see alteration down to 1,500 meters below surface. So it's pretty widespread, and nearly in all the district, you find something. Most of the mineralization, at least in the Candelaria deposit, is hosted in what we call a manto, which is a specific volcanic sedimentary unit where that is completely replaced or altered, and it has a lot of copper, forming some ore body that has a lithologically like continuous, which is sort of like a manto, which is a blanket actually in Spanish. So it's pretty literal. So in terms of mineralization, we find lots of it disseminated. We also see lots of it that is hosted in veins and breccia hosted. We see some timing relationships where mostly veining actually overlaps or cuts this disseminated mineralization, as we can see in this picture over here pretty well. In terms of mineralogy, nearly all the copper is hosted in the form of chalcopyrite. In terms of our iron oxides, we find mostly magnetite, but we also see a lot of mosquitovite, which is specular hematite replaced by magnetite. And we see some final veins in the system that mainly contain specularite, and sometimes they can also contain copper sulfides. So now we're going to go more to what we're going to be talking about today. So what we're trying to do in this, looking at the chemistry of minerals, you've been using them a lot to characterize fluids. The presentation actually gave last year was about pyrite chemistry. But in this case, what we wanted to see if we could have a better understanding of the evolution of the system. So we want to look at minerals that kind of like can give us information about time. In this sense, we know that magnetite and actinolite can occur in both early, intermediate, and main stage mineralization. And this is in more than one IOCG type. So I'm just showing here, this is Mina Justa in Peru, and this is Candelaria. And one can actually see, for example, actinolite in both deposits forms in different stages of the evolution of the mineral system. So does magnetite. So the idea is that the composition of these minerals maybe changes through time and space, and we can get more information about the deposit looking at these. So spoiler, yes, it does work. It works really well. And I'm going to not be talking about magnetite today, but if you want to learn more about magnetite, Maria Rodriguez Mustafa published last year in Economic Geology a great paper about magnetite in Candelaria, where there's a lot of information about the same subject. So we're going to be talking today about actinolite. So just actinolite, it's an amphibole silicate mineral. It's a solid solution, so we can have a magnesium and an iron-rich member. It mainly occurs in metamorphic environments, but we also find in hydrothermal alteration environments such as IOCG and IOA deposits. Here's a beautiful photo from the Candelaria deposit, actually, where we can see these really, really, really large actinolite crystals. And one thing that's very interesting here is that we have these pretty large crystals over here that are cut in this matrix that is altered, and it also has actinolite, but is fine grained. So this is actually telling us, this photo, immediately that we have two different generations of actinolite that are happening in the deposit. So again, we can think about that time idea. So what we did, we sampled actinolite from one drill hole in the Candelaria deposit that was over 1,000 meters deep. So it's a very deep drill hole. And we did a very nice systematic sampling of different actinolite grains. And we started looking at the actinolite grains under the SEM, looking at backscatter images, just to see what we could see, if they were zoned or not. We could see some differences in textures. And this was basically a leap of faith because we had no idea. And what we started seeing immediately were some very, very interesting textures. We see some replacement textures in some actinolite. This is actually one of the shallower one where we have, a replacement that is laid over here. You can see that is this more clear color in the grain. Then we see overgrowth where we see the core of an actinolite quite darker than the rims. And here we see an overgrowth of a different actinolite, and this difference in color is actually suggesting also a difference in composition. And then we also see some oscillatory zoning, as we can see in this crystal over here, where we see like this dark center, then a lighter rim, and then a darker rim. So what happens when we translate this into composition? We did WDS maps from these same grains to start looking at what these zonations were. And what we see is, yeah, they actually are chemically pretty well zoned. You can see here in aluminum, magnesium, iron. Again, here, these are pretty dramatical zoning, as you can see. And again, this oscillatory zoning is pretty strong. So this is great. This means that we actually are seeing variations in composition. And the cool thing that I just want to point out immediately is that generally early textures tend to have the same zonation. So in this case, we see the earlier core of this actinolite has higher magnesium. Over here, we see that the part of the grain that is not replaced has higher magnesium. And the same thing, I mean, the inverse thing can happen for iron. So this is good because, we have our timing already is working. So what comes next is that, we use this, a proxy for estimating temperature using iron and magnesium concentration within actinolite. We based this on a previous study done, published in year 2008 in Journal of Petrology by Haroldo Lledó and David Jenkins, where through experimental data, they were able to establish a polynomial regression that relates iron and magnesium concentration in actinolite with temperature. We use actually their estimations for 1 kilobar, which has been the pressure estimated for the Candelaria deposit. So what we did next is that we started applying this polynomial regression, but first to point data. So we did a lot of point spot data using electron microprobe. And so what we see is that the cores of these actinolite would tend to have way higher temperatures than the overgrowth. So this is kind of indicating that we have already two different generations with two different distinct temperatures. So in general, the grains of actinolite show a range of temperature. And if we actually plot that downhole of the drill hole, we systematically log, and we start calculating the average temperature for early textures. So this was, all the texture work that we did was pretty important. We can actually see that there's a positive temperature gradient downhole. So temperatures going up as we go down in the drill hole. The other thing is that we coupled these calculations with the grades of iron, copper, and gold of the same drill core, so downhole. And what we see is that iron is not coupled with copper and gold. So iron is just, really, they have a lot of iron in the deeper part of the system with no really good grades of copper or gold. And the other thing that we realize, and this is kind of like, it's not so convincing as this diagram, but it will be convincing afterwards, that when we have more copper and more gold, we tend to have a more scattered data of temperature. We tend to have lower temperatures in general. So we took this one step further. We already have the spot data of temperature, but we also have these WDS quantified maps. And in the end, these quantified maps, we can think of them as an array of quantified pixels that we can think about as point data also. So what if we try and apply this iron and magnesium temperature proxy to the whole grain map and see if we can actually get a temperature map for these actinolite grains? So it's just like a little schematic figure here showing kind of like what we're thinking about. Each one of these little squares here in this case would be a pixel. So we could actually try and calculate a temperature using each pixel of magnesium and iron and applying this polynomial regression. So in that sense, we kind of like use the magnesium and the iron map. Then we apply this polynomial regression using Python. So we don't have to do it pixel by pixel, what maybe I would have finished like in 10 more years. And what we get in the end are these absolutely beautiful actinolite grain maps where we actually see temperature. So each pixel here is related to a temperature in Celsius degrees. And this is fantastic because it gives us not only temperature information, but also a very graphical way of understanding how the temperature evolves in the system. So let's see the temperature maps that we got. We see strong variations within single grains. So in this case over here, which is the grain I've been showing quite a bit, temperatures go from 800 in the core to nearly 600 degrees Celsius in the overgrowth. And the error in these temperature calculations is plus minus 25 degrees Celsius. So they definitely do not overlap. And the cool, interesting thing here is also that the cores of these grains tend to be higher temperature. So again, we have that time idea working. We know that this temperature is higher in the earlier textures than in the later ones. But we also see hot, cold, hot fluctuations, sort of like an oscillatory texture, where we see a higher temperature core, then a lower one, then higher temperature again. So this is interesting also. So what we did next is that we treated these maps as data, spot data, and we started doing histograms to see how was the distribution of the temperatures map by map. And so what we see, there's two pretty nice examples that we can actually see two groups or clusters forming in some of these grains. In other ones, it's not as clear as you can see, but we have two really nice examples over here. So what we did next is that we just added all these point data of the pixels and did a histogram with a lot of data. And what we get is two very distinct clusters of temperature. We find a cluster 1 that is higher temperature. And if we look at the literature, it's also in a temperature range, which is where iron is soluble. So let's remember that diagram I showed before, where downhole with the temperatures higher, we tend to always see more iron. And we have a cluster 2 that is lower temperature, but coincides really nicely with solubility conditions for copper. So this is telling us that when we have, maybe a fluid in this temperature range, that temperature is kind of like in that sweet spot where copper is soluble within the fluid. And again, we know from all the work we did in textures that cluster 1 is earlier than cluster 2. So what are the implications for this? Well, we have to think a little bit more also about copper precipitation. We can look at this diagram from William Jones from 2014, and they have shown that fluids, when they cool down from around 570 degrees Celsius, this will start arriving. If the fluid is charged in copper, then copper will start to precipitate in the form of chalcopyrite. So in this case, in this sense, basically what we were seeing is that these actinolites from cluster 2 could represent a copper-rich fluid and potentially be responsible for mineralization in the deposit. And the nice thing here is that this also fits really well with the paragenesis and the deposit description that we've been working on. We know that we have an early alteration that is mainly actinolite and magnetite that we can maybe relate to our cluster 1, and it's more widespread. So probably this is alteration we're seeing deep in the drill hole where temperatures are higher. And then we also have actinolite that is very closely related to chalcopyrite and other sulfides. And this vein is a really nice example where you can see it pretty clear. So this could represent our cluster 2. So the nice thing here is that this micro-analytical data is actually talking with the rough description of the paragenesis and the characterization of the deposit. So we put all of this data together. And when I mean all of this data, this is not only this study, but this is the model I'm going to be presenting now, actually is an integration of a lot of previous work done by collaborators, by myself, and by other researchers. And we introduced this new genetic model for the Candelaria district that we feel, and we think we're really positive that can be applied to other IOCG districts, at least in the Andes and maybe around the world. So we can think about first an early stage. We know from our work that we have been doing, looking at pyrochemistry, that the main fluid source, at least for the Candelaria district, is magmatic hydrothermal. So in this sense, we have a magmatic system that will probably be having a cupola that is accumulating fluids, rich in iron, chlorine, probably copper, some sulfur. It's pretty hot. So we're talking about over 750 degrees Celsius. And it's basically controlled by faults. So this is the part where structural geology is also important. We have a set of sinistral transpressional faults, and every time we can think that these faults move, it will open space for this fluid accumulation to be able to ascend. So when the faults move a first time, what will happen, the fluid that will ascend will be hot, mainly charged in iron, too hot to carry copper, and it will have it will produce a widespread, mainly magnetite actinolite alteration. So this fluid accumulation can continue to happen. It may cool down. We also are really open to the idea that this magmatic system could be more dynamic, and it could be changing its composition. So maybe also the fluid accumulation could be more copper-rich or sulfur-rich. And what will happen, we will move the faults again, and the fluid that will ascend this time will be lower temperature, So copper will be able to be soluble. And once the fluid ascends, it starts moving through the fault system and it goes down that 570 degrees Celsius sweet spot, it will start precipitating copper. Then we will get to the main mineralization event, where again, the faults keep on moving and now our fluid is completely charged in copper, precipitating most of the chalcopyrite mineralization that we find in the district. So we know from also previous studies and characterization of the deposit that most of the mineralization of copper is related to fault systems or these more permeable lithological horizons, as the mantle that I talked about before. Also, we know that from in the later stages of the evolving system, there's already some interaction with external fluids that could be happening in this last stage of the evolution of the district. We also know, although, that these external fluids are not the main responsibles for mineralization in this particular place. So what are the implications for the IOCG and IOA model? Well, this actinolite magnetite mineralization stage that we're looking at the beginning actually falls within the range of iron oxide apatite deposits. I mean, the range of temperature and some of the mineralization style. So we can actually think about that maybe this early stage is more similar to an IOA mineralization style than actually what we currently understand by an IOCG. So if that is the case, the implication for the IOCG and IOA model I was showing before is that maybe these magnetite actinolite early alteration stages in IOCG deposits are more similar to what we understand for an IOA. And in that sense, the IOA would not be the roots of the system, but actually be an early event that is then overlapped by this main IOCG event. So we have an early iron-rich event overlapped by a copper-rich one. So in summary, what we can say from this is that IOCG and IOA deposits are not only related by depth of emplacement, but also by changes in the hydrothermal fluid reservoir. We've seen here changes in temperature, but again, we also think that potentially there's changes in composition. And if you start looking at in the literature in general, these large and economically important IOCGs tend to have this early barren iron phase. And maybe that could be suggesting us that that early iron phase that is barren is necessary for the copper precipitation or copper formation. These are two photos from the Candelaria deposit that are pretty interesting because we actually see chalcopyrite replacing magnetite, which leads us to think that maybe the precipitation of magnetite could be important also for copper precipitation. So what comes next? I think this is a great example of dumpster diving in general, because it's really interesting to be working with these non-economically attractive minerals such as actinolite. So looking at the garbage can be pretty useful sometimes. And I think it opens the door for a lot of new questions. So some of the most obvious one is, can we distinguish between these early and main stage actinolite events, but with other elements, not only using temperature? The second one is, can we actually use this distinction as an exploration tool? Maybe we can actually think about actinolite as being one of these mineral pathfinders that will help us understand if we're close to an IOA or close to an IOCG event. And if the temperature changes that we observe in the Candelaria deposit, is this the norm for other IOCG deposits? Well, this we have to see also. This is one first try to get closer to that idea, but we're pretty positive about it. And the last one is, do we know the timing between these events? And this one is actually coming soon because there is currently a student working in Michigan that we're all collaborating together, looking at the geochron of these very particular and distinct hydrothermal events or pulses with very positive outcomes in terms of the difference in time. So again, thank you very much. If you have more questions, more specific, we have this very new paper in Nature Communications, Earth and Environment. And as a bonus, we really like mineral chemistry, especially we can apply it as a geothermometer. And just last week was published another paper looking at magnetite thermometry by the same research group in Scientific Reports that could be very interesting to look at. So with that, thank you very much. And I'm very happy to receive questions and start the discussion part of the presentation.
Thanks a lot. It's really cool. I mean, it's a bit of a dumpster mineral, and I work with it a bit in the oceanic realm. And there's almost no limit probably to what it can take in and what you can measure with a sensitive enough laser or whatever.
Yeah, it can be a little bit overwhelming. So I think there's a challenge with that also.
Yeah. I mean, the titanium in amphibole thermometer, which is popular in metamorphic circles, I think I mentioned it to you before, it comes immediately to mind. I get titanium and iron substitute for each other and lots of things. So perhaps it's the same mechanism. Might be worth looking at. I saw you'd already plotted titanium and it was going high. So there's something there. I think a strongly shorter wave infrared active mineral has several different absorption features that you can measure with standard instruments. And I bet some of them vary with iron to magnesium content. So from an exploration point of view, mapping out bulk iron number for actinolite would probably be pretty feasible, although maybe I just shouldn't say anything more.
No, that's actually a great comment, because it's part of, what we aim is to kind of like make this tool. And one of the main things, if you want to use this as a tool, actually be able to use instrumentation that is not as large and complex as a laser ablation ICP-MS. And maybe shortwave would be way easier to think about something that you can use in the field. So yes, that's kind of like what we're aiming for in the future.
Perhaps, yeah. I see Anne's on the call. She probably have something to say. All right. So let me find. Here we go. Neil, have you got a question queued up there? I see. Oh, lots of questions.
Between fluor-rich apatite and chlorine-rich apatite, that tell us if the source is more hydrothermal. And that has been published a couple of years ago by Gisela Palma. And there's a lot of information on that. It's more challenging in IOCG deposits because they do not have that much apatite. We tend to see it, at least in Candelaria, in the SEM sometimes. So I think it would be challenging to try and use apatite to connect both deposit types, because it's more like a sometimes rare alteration mineral in IOCG systems. But yes, in IOA definitely there has been work on that subject that has been previously published that has been gotten some pretty useful results for understanding the evolution of those systems.
Okay. Yuri, would you like to take on the next question?
Yes. So I guess the question from Jeffrey Hedenquist, are there any difference with the older gray-metal proterozoic deposits that you showed in your earlier slide? And also, what are the most common deposits of this style, much older? Why? And why do we see these younger examples in Chile and Peru? Any comments on this general aspect of Earth evolution? It's kind of
yes,
broad question.
Those are all great questions. So we haven't seen or compared with older deposits. Not because we don't want to, it's because we just started with this work. And I think we have in mind to be able eventually, start looking at the older deposits. Right now, we're starting with the Andes because it makes sense, at least more sense to us to think about, deposit scale, district scale, maybe Andes scale, that everything has the same age before moving to the older deposits, but not because we don't want to. So we don't know yet if it's similar, or because they're older, maybe we're not going to be able to see these very distinct changes because alteration is stronger, deformation is stronger, so we don't know. In terms of why we see the distribution of the ages in the IOCG deposits, there's a paper published by Dave Groves in 2010 that has this that has been used a lot, this diagram where they show the different IOCG deposits. And basically he suggests that the main thing they have in common, not trying to look for a specific tectonic environment where they form, is actually that they have more interaction with the sublithospheric mantle. So in that sense, you have more interaction with your mantle. And in this case, in Chile, specifically, this is also happening for these deposits at the specific time when they form. I did not mention this in the presentation, but between the late Jurassic and lower Cretaceous in our western margin of the Andes, we actually have mainly extension because there's back arc extension because subduction is too steep. So we have subduction rollback, and that's going to be opening our back arc, and therefore our crust will be thinner. And in this, thinking about that may be also the common thing we find between these deposits and the older one, is that we're having more interaction with more mafic and primitive magmas because, your crust is thinner. And there was just a very recently, maybe less than a month ago, a paper published looking at zircon chemistry, characterizing the crust of the Andes between, I think, 140 and something like 70 million years. And they show that they can actually see how the crust is thinner and how you have more interaction with the mantle. So I would think that is the common thing we can find between these deposits, and maybe that's why we have this much younger part of the world with IOCG and IOA deposits.
That's great, Irene. And it's a great segue to like a combination of questions that I'm going to ask next, because I do remember another talk you gave in 2019 at the SEG conference in Santiago where you talked about mafic rocks, didn't you? Right? And so there's a couple of questions here, like, for example, are these invoked parental magmas for these different deposits or districts distinct from those related to other ore-forming magmatic systems? And then another question from Hubert would be, what could be the reason of temperature changes in the hydrothermal reservoir? Could uplifting of the magmatic chamber explain this? And then I think I'll leave it at that for now.
Yes. So just starting with the second question, I mean, in general, we've never seen these parental magmas. That's one thing that we have to keep in mind. So we assume they exist because, other works in mineral chemistry are telling us that these deposits have a magmatic hydrothermal origin, but we've never been able to actually get a sample of the magma, responsible for the fluid source. So in that sense, it's very difficult to have a good understanding what is the composition exactly of this magma. But we do know from pyrochemistry and some isotope work that it has a more mafic or more primitive signature. So that's the information we have respect to these, potential intrusive bodies that we assume or interpret that exist. And the temperature, that's another really good question. So in this case, what I was showing you here, we actually still did not have an understanding of time. So our first idea was that, if the reservoir starts cooling, then, just because of time, then the fluids will start cooling also. So each time you sort of like tap the reservoir, the fluid that will ascend will be cooler. But I think with some new data we're gathering, where we're seeing that these events could actually have more than 1 million years of time span between one another, we are more, towards the idea that actually there's also a big change in the composition of the magmas that are being tapped and of the fluids that are being tapped. I do not know the answer for the second one, if this could be, the magma actually ascending and uplifting, if that could be the reason of the cooling. It could also be like, I don't know the answer, so I'm gonna let that one pass.
Okay, Yuri?
Yeah, I have a follow-up question to this, which I think nicely tailing the previous, from Kurt Dollerstrup. Is there interest in sampling discrete isotopic ages across each of the thermal zones to provide another verification for the thermal and mineralization history?
Well, that's sort of what I was mentioning before. So that is work that is currently in process. But what we've been doing is that we're actually been dating different mineral systems to see if we can see this evolution also in terms of time. This includes magnetite, apatite, actinolite, titanite. So we've been using different mineral systems to be able to constrain this thermal evolution with time. This is work that is being done by Daniel Blakemore in Michigan University, that he's going to publish it this year with those results.
And I have a kind of indirectly related question, more technical one. This thermometry that you used for actinolite, how precise that is? So like each point plus minus what?
Yes.
30 degrees?
So I mentioned it very briefly in the presentation, but it changes, like the calcium concentration is like either plus minus. And the maximum you can get is an error of plus minus 25 degrees. So that's the error that we used for all the calculations. And we were very concerned that we could actually find clusters that were not overlapping in that plus minus 25 degrees.
Okay. Neil?
I've got some questions here, which are definitely from Chilenos and who understand, who want to know some more details about the district. So part A from Ricardo Ardilla is, what is the genetic relationship between the upper skarn and the underlying IOCG mineralization at Candelaria? And then Marcos Valencia asks, what, in your opinion, what is the relationship of La Botón del Oro in this context?
For the first question, that's work in progress also. I have not been working in the skarn deposits in the district, so I'm not completely sure. Actually, I have an idea to be able to also, look at samples from the skarn to see if we can see any differences in their actinolite composition. I strongly suspect that it's part of the same mineral system. They're not two independent events. I'm not a big believer in coincidence, at least in that case. So I'm pretty sure they are related, but I would be, I don't know how yet. And for the second one, I do not know El Botón de Oro, so I would probably need more specifics on that question, as I'm not, my knowledge on the specific deposit is zero.
Okay, I guess we'll leave the specifics for like, hopefully you can communicate with Irene afterwards. Yuri, back to you.
Yes, so I'm going to read the question from Apoliana Hiring. Congrats on the talk and paper. Have you worked with stable isotopes to compare possible different sources of the fluids or mixing of the sources of either for actinolite? Would fluid mixing theory is possible for temperature changes? And I guess that's overarching, actually, my question. Where are the fluid stable isotopes used for sourcing the fluids?
We haven't done an actinolite because we would actually need in situ isotopes, because as you can see, the grains are very zoned, compositionally zoned. So, and right now, oxygen isotopes, which would be our first choice, we're still working on finding a place that actually does in situ oxygen isotopes. So it's normally the whole grain. So in that sense, we will start getting, mixed signatures if we did that. But we have done isotopes in pyrite. We have done sulfur isotopes in pyrite, bulk and in situ. So we have a good understanding in that. And what we see, and this is a paper we published last year in Economic Geology, that we see that, again, we see the zonation in terms of isotopes in the pyrite, sulfur isotopes. And after a very, a hard work getting samples, all the late samples in the system, all the later veins tend to have higher or, higher numbers for sulfur isotopes. So what we interpreted from that work is that, yes, we do have some external fluids participating in the party, but they're arriving really late. So basically the later samples, what I showed before, these like late speculite veins that sometimes have some sulfides, those are the ones that are given the higher numbers for the sulfur isotopes, which is why we interpret that as external fluids are a later event, and we do not consider them that important in the system or that important to be able to lower the temperature that we're seeing in the actinolite precipitation.
Okay, a couple of more questions here, all sort of related on the mineral chemistry front. A comment from Dave Lentz suggesting that magnetite and apatite are plagued by what he calls DRP reactions, which I'm not too sure what DRP stands for. Would amphibole be robust, or do we need clarification what DRP is here? I
think is the solution reprecipitation.
Yeah,
maybe
it is. Yeah.
We do see some problems with that, and we've been looking at that with the trace elements. Especially we find it when we find replacement textures. We actually do find that, but the trace elements are great because they're showing us. We'll be doing some principal component analysis with the grains, and they're actually throwing a whole cluster that are the grains that have problems, that kind of problem. So we can actually take that apart and work with the data that is cleaner and better quality with none of these problems. So yeah, what we're seeing, we're still seeing the same things that we're seeing with the maps. So we do think that the amphibole is robust because we actually found a way of taking into account these data points, or all the data that could have that problem that he's talking about, the solution, reprecipitation.
Excellent. That's what I wanted to hear. Thank you.
Yeah.
Excellent talk.
And following from that, I'll combine a question from Jeff Hedenquist and one from, first I'll start with Jeff's, which is basically, do you see any evidence of ilmenite? Others have suggested that cooling of ulvismanel plus CO2 evolves to magnetite and also to ilmenite. Is there a role for carbon dioxide based on any of your observations in this?
We do see some ilmenite, but in the deeper samples. And that is something that was published last year in Maria Rodriguez Mustafa paper in economic geology, where she worked with magnetite, and she takes into account the ilmenite. So there are some ilmenite. So I invite you to read that paper that has some pretty interesting observations. And what she interpreted is that the ilmenite was exsolved from the earlier higher temperature magnetite. So the second part, in terms of role of CO2, that's a great question. We have been thinking a lot about CO2, but not that hard to already have an opinion about it. I know CO2 is interpreted to be higher in IOCG deposits, and so I think it's a really good observation, and maybe some of the processes or even key processes could be related to the role of CO2, but at the moment we haven't done any work on the subject, so I wouldn't know to answer that correctly.
Okay, well, I'm going to tell with the next question from Gustavo, that he's saying that they see in the Peruvian deposits, they see that the Peruvian deposits are rather more complex, with the reduced pulses occurring with pyrrhotite and arsenopyrite, and temperature decreases to epithermal conditions. And they also,
well, in that sense, yeah, so in general, we also actually have some periodite in Candelaria, and we know that the changes in redox are pretty extreme, and that's something that we're working on at the moment, looking at the trace elements in actinolite, looking at the elements that are redox sensitive. And just as another spoiler, we are seeing some ways of clustering actually the composition of actinolite just looking at redox. So it might be also possible to pin down what parts of the actinolites are are more oxidized or more reduced. But in general, we even just by a point of view of looking at the paragenesis of this type of deposit, we do see that we have mosquitovite, magnetite, and specularite. And we have each of these iron oxide replacing each other, which is already a direct message that we have a lot of changes in redox. And we still are not sure how important these are for copper precipitation, but I suspect that they are important, that they have a role in the whole system. So that's more work to think about. And the part of temperature decrease into epithermal conditions that are gold rich, I haven't seen that in Chile, but I would love to see it in Peru maybe someday. But all of these are things to take into account when we want to think of the processes that are responsible for the evolution of this type of mineral system.
With that, I think we've gotten a lot of the questions done. Tom, would you like to close us out?
Maybe I have one or two. How you doing, Irene?
Oh, good.
A few more?
Good. I had lunch just before the talk, so I'm energy high. I keep on going.
Okay, I'll start with a fun, easy one. I think a lot of interest in IOCG in recent years has been about the rare earth element content and maybe critical metal content. You mentioned it in your introduction, probably based on Olympic Dam, right? Is there also significant amounts of REEs or anything apart from, iron and copper in these Chilean deposits?
Yeah, so, there's not that much REE as compared to Olympic Dam. We do, for example, see quite a bit of scandium in amphiboles, enough to be economic if one could think about it. But so I think there is a lot of potential we want to think about the future of looking at, maybe amphibole in that sense, but always there's the other part, the geomethodological part can be so complex that, one has to be careful when you say like, yes, this is the future, I don't know, of scandium. We always have to think of how we're going to get the scandium out of the mineral. And in that sense, we do find a lot of cobalt in these IOCG deposits, quite a bit. It's nearly all contained in pyrite, and it's nearly all contained in the structural and the atomic structure of pyrite. So again, in that sense, the metallurgical processes to get the cobalt out is really challenging. But it's all, I'm pretty sure there are a lot of companies that are looking at the cobalt more specifically as something that could be economically viable in IOCG deposits here in Chile.
Okay, cool. Yeah. And then, so the other thing is, we've had quite a few talks on the IOCG IOA family. We even have our own archive channel for that on ODH. And a couple of prominent ones, from Adam Simon way back last year, of Fernando Tornos, and Dave Lentz, actually, although that one's not recorded. They present different models, but the common thing about them is that magmas are directly implicated in, the ores are magmas, basically, in these. And whereas in your synthetic model, those were mainly focusing on IOA, I think. But in your synthetic model, the IOA deposit was underneath the IOCG. How should we think about those other interpretations relative to yours? Are those where the IOA portion of the system has come up to the surface? Are we just looking at different depths potentially of a consistent model, or are they opposed?
So I think the main thing is time. So we're not thinking about a single fluid that evolves from an IOA to an IOCG. I mean, that could happen, but that's not sort of what I'm proposing. Here we're thinking of distinct pulses, like telescoping. You have your IOA. I have no problem with all the other models, but the system evolves. So that's the thing, it evolves with time. And I think that's the key thing here is that we're thinking about a mineral system that is dynamic, that is evolving with time. So you can start with something more magmatic, and as the system evolves, that could be superimposed later by something that is more hydrothermal. So this is not a single fluid that evolves. This is actually a dynamic system that its composition could be evolving with time. And again, I really like the idea of tapping the source. Each time you tap the source, your source could be changing. So that would be the main difference with this model. So I'm not saying you definitely can find, this idea of a fluid evolve into something more copper rich or sulfide rich. That happens. And you see IOA deposits where the later stages of the deposit tend to have veinlets that are sulfide rich. Not much, not to think that, it's economically viable or anything like that. But systems evolve to that. So there's clearly an evolution in that sense, but I think time and a dynamic source, that is the key of what I'm showing here and the main difference. So in that sense, I don't see a problem with all the other OA talks. We can all be friends and work together.
Okay, I like that as a place to end. I know there's some good comments going in the chat there, but this will work well for the recording. So I'd just Neil had to take off, but I'd just like to thank you on behalf of Waterpods Hub for your second grade talk and also all your work hosting with us. It's been fantastic. It's been a really good journey the last year and a half, despite the circumstances. And yeah, it's a great paper, and that was a really polished, good talk, good story. So thanks from my side. Yuri?
Well, I thank all the participants for signing up today, and I really enjoyed the talk. Irene, I thank you, and I thank you on behalf of all the viewers.
Yeah, thank you guys for the invitation. And again, stay tuned. There will be more things and really fun things coming out on the same topic. So we'll let you know.